In this lecture, we will discuss about the maximum power transfer theorem and its proof. This lecture covers the introduction to the maximum power transfer theorem, proof of the maximum power transfer theorem, and steps to solve a network using maximum power transfer theorem. Maximum power transfer theorem is one of the important theorems of the electrical systems. It has its own significance and own importance in the electrical systems. The main use of maximum power transfer theorem is in communication systems. Now, maximum power transfer theorem basically deals with the transfer of the power from source to load. Means how much maximum power is transferred by source to load. Load is one very important parameter in the electrical circuits, and the power which is delivered by source is basically consumed or utilized by the load or dissipated by the load. So what is that maximum value or maximum power that is dissipated by the load? That is concept is basically understood by maximum power transfer theorem. As per the statement of maximum power transfer theorem, the maximum power is transferred from source to load when the load resistance is equal to Thevenin's resistance of the network. That means when the load of the network becomes equal to the internal resistance of the network. Thevenin's resistance is sometimes also known as internal resistance of the network. So when these two resistances match or are equal, at that point of time, the maximum dissipation of the power is made by load. You can understand it in any way, whether you can say that the maximum power is transferred by source to load, or you can say that maximum power is dissipated by load received from the source. So as per the statement, when RL is equal to RTH, at that point of time, the load resistance means when load resistance is equal to RTH, at that point of time, maximum power is transferred from source to load. So if we consider one circuit as shown here, in this circuit we have a load resistance connected across the load terminals, and this may be a complex circuit here which is represented with the help of a block diagram. So we need to find out the Thevenin's equivalent of this particular network, and Thevenin's equivalent contains two components, VTH, which is Thevenin's voltage, and RTH, which is Thevenin's resistance. So when these two resistances are same, they match. So at that point of time, we can say that maximum power is transferred. So that means if it also indicates one thing, that if RL is greater than RTH, so no maximum power. If RL is less than RTH, then also no maximum power. So that means maximum power will only be dissipated when this condition is achieved. So let us prove this condition. Now we have the Thevenin's equivalent of the network, which is VTH and RTH, and then we have the load resistance across the load terminals. This is RL. Now in this circuit, RTH is generally fixed and RL is variable, right? Now, the condition of RL is equal to RTH is now proved here. So let us prove this condition. So the power dissipated by load is given by, let us say it is PL, which is given by IL square into RL. Means whatever current flows, let us say IL current is flowing in this load resistance, and because all these three components are in series, so the same current is flowing in all these elements, right? So the power is basically I square R, right? So now this is, let us say, equation number one. Uh, the load current IL is, if you apply KVL in this particular mesh, if you apply KVL here, you'll get IL is equal to VTH by RTH plus RL. Now this is the Thevenin's equivalent basically. So we can use the same formula for the load current also. So we will substitute this value here. So we have PL is equal to VTH square divided by RTH plus RL square into RL. Now this is, let us say, our equation number 2 here. Now we can, if we need to find out the maximum power, if we say that this power is maximum at some point of time, so we need to apply the condition for maxima. So this condition for maxima is basically the first derivative of this load power with respect to the variable. Now variable here is load resistance. So we will take the variable with respect to this. So should be equal to 0. So when this condition is achieved, so we will see what is our result. Now dPL by dRL. So let us get its derivative. So it is VTH square will be taken outside. So we have RTH plus RL raised to the power 4, and then we have RTH plus RL square into 1 minus RL into 2 RTH plus RL, and then bracket close. Now we will simplify this equation. So this is because equal to 0, so we will put it equal to 0. So now this equation will be simplified here, or so these two components will be, cancelled out here, means they are 0. So we have RTH plus RL whole square minus 2RL RTH plus RL is equal to 0. Now we will take this component as common here. So we have RTH plus RL, and then we have RTH plus RL, and then we have this one minus 2RL. It is equal to 0. So, so we are simplifying this one, and this is RTH minus RL is equal to 0. Now, because if you put this equal to 0, RTH plus RL equal to 0, so it would be RTH is equal to minus RL. So resistances generally are not negative basically. They cannot be negative, right? So this cannot be equal to 0. So RTH plus RL cannot be 0. So hence RTH minus RL is equal to 0, or RL is equal to RTH. Now, if you see this equation, this is proving that the condition which we took, the condition for maxima, means we kept the first derivative of load power dissipated by the load basically with respect to RL equal to 0. So by doing so, we have reached to the solution that RL is equal to RTH. So this proves that the maximum power is dissipated by the load when RL is equal to RTH. So this is the condition for maximum power transfer theorem. Now let us see the efficiency basically. What will be the maximum efficiency of the circuit in this condition? So let us understand efficiency of the network. Now efficiency is generally represented with neta, which is equal to output power to the input power. So which may be written as PL divided by PS. Now PL is equal to IL square RL, and PS is equal to, if you see the circuit diagram here, so PS is basically the power delivered by this source, right? So this source will deliver power into the whole network. So we will consider both the resistances here. And because all these three components are connected in series, so we have the same current flowing in all these three components, VTH, RTH and RL. So IL square into RTH plus RL. So if we substitute these values here in this particular equation, so we get neta is equal to uh, IL square RL divided by IL square into RTH plus RL. Now we will apply this condition, the maximum power transfer theorem, which is RL is equal to RTH. At this particular condition, neta is equal to, so here IL will be cancelled out, right? So we will write it in terms of resistances only. So let us write it here itself. So we have RL divided by RTH plus RL. So if we replace this RL with RTH, so we will get RL divided by RL plus RL. We can also write or RTH divided by RTH plus RTH. We can replace anything. So it would be equal to RL by 2 RL or equal to 1 by 2. So it is 50%. So that means the network when in which the load is dissipating the maximum power, the maximum efficiency would be 50%. So from here we can say maximum power does not mean maximum efficiency, right? So let us understand this concept in more elaborated way. Because the load power is equal to your IL square into RL. So if you see here, so let us apply two conditions here, extreme conditions. One is if RL is 0, then PL is 0, right? The B condition is if RL is infinite. So if RL is infinite, then IL is 0, hence PL is 0. Now what does it mean? It means that you have two extreme conditions taken, this one and this one. So if you keep the load resistance at low value, even then the power dissipated by the load is minimum or ideally zero. If you keep the load resistance maximum very high, even then also the power dissipated by the load is minimum. So that means the maximum power is achieved somewhere between these two extreme values. Okay. So from this case, we have seen that the power is minimum for the two extreme cases of RL. So hence, to justify the statement of maximum power transfer theorem, we can say that the maximum power is transferred by the source to load, or the maximum power is dissipated by the load is when we have some inter, or you can say some value of RL in between 0 and infinite, right? So you can also understand this with the case that if you see here in this case, if you take this equation once again, so if RL increases, your PL also increases, but IL decreases, which affects PL. So this will not let to increase the PL. Similarly, if RL decreases, PL also decreases, but IL will increase, which again affects PL. So that means we need to get some uh, intermediate value of RL so that we can get the maximum power, right? Because in this equation, if we see, when one parameter is increasing, the other parameter is decreasing, which is affecting the load power, right? So let us understand this with the help of a graph basically. So let us plot the graph between PL and RL. So if we plot the graph here, so this is, let us say, RL, and this is, let us say, PL. So as per the statement and as per the previous analysis, we can say that the power will increase to certain value of the resistance, and this power will be taken as the maximum power, and the value of resistance at which you get the maximum power is RL is equal to RTH. So from this graph, we can say here we have RL less than RTH, and here we have RL greater than RTH. So in both the cases, the power is reducing, as you can see, but the maximum power is here. which is 50% only efficiency, right? So we also need to understand what is the maximum power dissipated by the load, right? So the maximum power dissipated by the load can be calculated by using the same formula. PL is equal to IL square into RL. So we can write it as the same equation, VTH divided by RTH plus RL square into RL, right? So at RL is equal to RTH. So PL is maximum or P maximum, whatever you can write. So it is, so we'll simplify this one, VTH divided by RL plus RL, and this is square, this is also square into RL. So PL max is equal to VTH square divided by 4 RL. So this is the maximum power dissipated by the load. So how to apply MPT theorem. So first thing that you need is determine the Thevenin's equivalent of the given circuit. So this is what you have to do first of all. The second point is at RTH is equal to, sorry, at RL is equal to RTH, calculate the load current. 3, calculate the value of PL max using formula VTH square by 4RL, or also the power delivered by source at RL is equal to RTH, that is P max is equal to VTH square by 4 RTH. So this is how we can calculate the maximum power transfer by the source to load, or maximum power dissipation by the load using this particular theorem. So this is it for today's lecture. Thank you so much.